Simpson's rule is a technique by which we approximate an integral using, instead of rectangles or trapezoids, arcs of parabolas. One important thing to note for Simpson's rule here is that the arc of the parabola is going to be defined by 3 points. And in the first segment here, we've got p sub 0, p sub 1, and p sub 2. And they're associated with x values of x sub 0, x sub 1, and x sub 2. Between any two subsequent x values is h. And in what follows, h is going to be what becomes delta x. So what do you mean what follows? I mean, we're going to develop Simpson's rule using the idea of these parabolas. For that, we're going to use a different diagram altogether. Here we have a diagram that represents the arc of a parabola that has the y-axis in the middle of it, right? So to the left, you have our value of negative h. To the right, we have our value of h. You'll note that the vertex is not on the y-axis, and that's totally irrelevant for what we're doing right now. We're going to say that the equation of this parabola is y equals ax squared plus bx plus c. And the area underneath this parabola from negative h to h is equal to the integral from negative h to h of the quantity of ax squared plus bx plus c dx. Now we're going to split up the terms of this integral in what may be a weird way, but it'll make kind of sense in a minute. Negative h to h, the integral of ax squared plus c dx, plus the integral from negative h to h of bx dx. Now the reason we did that is because bx is an odd function, and we're talking about the integral of an odd function with a symmetric interval. That portion, that whole integral from negative h to h of bx dx is going to be 0. Likewise, ax squared plus c is an even function, and so we actually can take advantage of symmetry and say that a is equal to 2 times the integral from 0 to h of ax squared plus c dx. Integrating that using the power rule is going to give us that a is equal to 2 times the quantity of 1/3 ax cubed plus cx, and that'll be evaluated, from 0 to h. Now substituting h in place of x, and then at the same time distributing the 2 and factoring out a 1/3 is going to give us h over 3 times the quantity of 2ah squared plus 6c. And yeah, right now it's like, so what? Who cares? This is leading to something. So we'll just set that aside for now. We'll go back to our diagram here, and we see that the parabola passes through the points p0, which is negative h y sub 0, p1, which is 0 y1, and p2, which is h y2. We're going to use these points in the equation for the parabola, y equals ax squared plus bx plus c, and we're going to come up with another way to express the area under this curve. So using these points, when y is y naught, we have that h is, or negative h is the input, right? So y naught is equal to a times negative h squared plus b times negative h plus c. y1 is the output when x is 0, and so we end up with y1 is equal to c. And when the input is h, the output is y2, so we get the equation y2 is equal to a h squared plus bh plus c. Now at this point, what I'm going to do is I'll tell you that we're going to build the expression 2ah squared plus 6c that we came up with by integrating using these equations that we just wrote down. To build the expression, almost forgot that build has a u in it. Jeez. Anyway, to build the expression 2ah squared plus 6c, we're going to multiply the second equation that we're looking at y1 equals c by 4 on both sides, and then add these equations together. So multiplying by 4 on both sides, we get 4y1 is equal to 4c. Adding together on the left-hand side is not going to do us many favors here, but it's y sub 0 plus 4y1 plus y2. Adding on the right-hand side, we have ah squared. I mean, it's negative h squared, but when you square it, it becomes ah squared. Ah squared plus ah squared is 2ah squared. B times negative h plus b times h, subtract out. And boy, b just got the short end of the stick in this one, didn't it? And then c plus 4c plus c gives us plus 6c. And what we've just done is we've built the expression that we came up with by integrating, but now we have it in terms of y values. With that as our foundation, we can say, repeating the process for the subintervals from a to b yields that the integral from a to b of f of x dx is approximated by s sub n, where s represents Simpson's rule, n is the number of subintervals, and it equals delta x over 3 times the quantity of f of x sub 0 plus 4 f of x sub 1 plus 2 f of x sub 2 plus 4 f of x sub 3, this will end, don't worry, plus plus 2 f of x sub n minus 2 plus 4 f of x sub n minus 1 plus f of x sub n end bracket. There's a pattern in the coefficients here that I'll write down, and then we'll talk a little more about what we just saw. The pattern, as you can see from the first few terms, is 1, 4, 2, 4. So it's 1, 4, 2, 4, and it continues on bouncing back and forth between 2 and 4 until it gets to 2, 4, 1. For the trapezoidal rule, you may remember it was 1 and then a bunch of 2's and then a 1. Here we're bouncing back between 2's and 4's. Now, where the heck did all this come from? Well, folks, when we did the integration, right, we found h over 3 times the quantity of 2ah squared plus 6c. That h over 3 is what became delta x over 3. As for the rest of it, when we added these equations together, we have y sub 0 plus 4y sub 1 plus y sub 2. So that's where the f of x sub 0 plus 4 f of x sub 1 is coming from, right? That is y sub 0 plus y sub 1. But then what's up with this 2 here? Well, folks, just as with the trapezoidal rule, the function height at x2 is repeated. It's repeated once for the parabola arc on the left and once for the parabola arc on the right. I put a 1 and 1, and I meant a 1 and then a 2. And then the function height at x4 is again repeated. It's used once for the parabola arc on the left and once for the parabola arc on the right. So the coefficients would be 1, 4, 1, and then 4, and then 1. But the ones interior, right, the interior parabola arcs are getting used twice. So it's kind of like 1, 4, 1 for the first parabola arc, 1, 4, 1 for the second parabola arc, but that line, that vertical here at x2 is being used twice. Just like you saw with the trapezoidal rule. Now I'm not done here. We've got to say where n is an even number. So n is even, and delta x is equal to b minus a over n. N has to be an even number for the pattern to work out correctly. If n were odd, we'd end up with like 1, 4, 2, 4, 2, 2, 1. It wouldn't end correctly, so n has to be an even number. As with the trapezoidal rule and the midpoint rule, there is error involved in using Simpson's rule. And the inequality is that E sub s in absolute value, so the error for Simpson's rule, is less than or equal to k, same k as before, times the quantity of b minus a to the fifth. Now that's a bigger value, but it's divided by 180 n to the fourth. Excuse me, I said it was the same k as before. That's not true at all. As with the trapezoidal rule and the midpoint rule, there is error involved in Simpson's rule. For Simpson's rule, the absolute value of e sub s, right, error for Simpson's, is less than or equal to k times the quantity of b minus a to the fifth divided by 180 n to the fourth. But this time, it's the fourth derivative of x in absolute value that's less than or equal to k for the x values between a and b. So instead of the second derivative, it's the fourth derivative. B minus a to the fifth is bigger than b minus a cubed that we saw in the other two rules, but the denominator is 180 n to the fourth. This thing gives you a lot smaller margin of error for the same value of n, is how this works out. I'm not going to go through an example of Simpson's rule in any videos because it's just like what you saw with the trapezoidal rule and the midpoint rule, and you are welcome to use Excel to do the computations.